Hello there, kiddos. This is Mr. Gilmore with the 1.7 Algebraic Postulates. So, in our last lesson, 1.6, we looked at geometric postulates and we talked about what a postulate is and what it does for our system. So, now we're going to continue on with our next set of postulates known as the algebraic. So, we're going to be seeing many of the algebraic postulates, which also end up on your postulate theorem handout. But also, we'll practice doing some inferencing with postulates, and at the very end, we're going to see something new. We're going to see what's called an inference chain or an inference table. It's the idea of what if we can actually draw more than one inference and continue drawing inference as we continue with making statements and justifiably. Making statements with using either our definitions to justify or our postulates to justify. So let's take a look. We'll look at several postulates to begin with, all algebraic in nature, and then we'll jump into looking at some examples to make some inferences. So our very first postulate, it feels like this first one is a bit trivial, but it's actually not. It's actually, we'll use this one quite often. This is called the reflexivity of equality, or ROE, R-O-E. And this is what it says. For all x, x is equal to itself. X is equal to x. So every quantity is equal to itself. 1 is equal to 1. Measuring A B C equals measuring A equals C. Aristotle equals Aristotle. We'll actually be looking for equalities in our next chapter. And as we, in chapter 3, and as we hunt down those equalities, what we'll be thinking about is using these. And so at any point in time, we know a quantity is equal to itself. We're actually going to take full advantage of that, knowing that it's equal to itself. And so reflexivity of equality does come in handy quite often. Next, we have transitivity of equality, or TOE. You may recognize this one. Here's what it says. That for all values of x, y, and z, that if x equals to y and y is equal to z, then x is also equal to z. You may have actually seen this in a previous class in your mathematical history, in your mathematical career of schooling. And so we actually use this one quite often as well. What you're noticing then is we are upgrading the amount of equal relationships we have here. We're actually taking two equal relationships, x is equal to y and y is equal to z, and we transform that into a third equal relationship, x is equal to z. Down below, you see that if AB is equal to EF and EF is equal to IJ, then AB is also equal to IJ. Now, Euclid had a different formulation. He would say this: things equal to the same thing are equal to one another. So the last example down below, if x equals z and y equals z, then x is equal to y, because x and y are both equal to the same thing. So whether we treat it as Euclid's formulation or not, it still will hold the same property, that we're bringing two relationships of equality together to form a third relationship. Substitution property of equality. Let's say now that we have two quantities we know are equal to each other, such as x and x is equal to y. Then this is what this property lets us do. For any time I encounter an expression or equation where x occurs, then I can actually replace that x with y, and also vice versa. I can actually take y out and replace it with x, because I know that my substitution property holds. So think of this as just like any sporty event. If you were to have a quarterback in the game and the quarterback gets injured, you want to substitute in another quarterback because you want your quarterbacks to have equality there, right? You would not put a running back in for your quarterback. So down below it says if x equals y and if x equals y and x is greater than z, then I also know y is greater than z, because I can actually take I can take x out of the inequality and replace it with y, because we know that x and y are equal, so they're interchangeable. Down below, if x is equal to 180 divided by 2, then I can also replace the expression on the right-hand side with the value of 90. Why? Because we're actually substituting in the measure of 90, because we know that for 90 degrees is equal to 180 divided by 2. So it's really simplifying as well. So anytime you simplify an expression, you're going to be using what we call the hammer of substitution here. So when in doubt, use the hammer of substitution, okay? It is mere replacement is what we like to call this one. It's merely replacement. So you replace one expression with another. Now, transitivity and substitution can get confused quite often. Well, let's make a couple statements about those. First of all transitivity is substitution. So anytime you encounter transitivity of equality, it is identical to substitution as well. So it says, let's say we're given that AB is equal to CD and that CD is equal to EF. Well, then obviously by transitivity, we can conclude that AB is equal to EF. But we also could have concluded the same thing, but by substitution, because we can think about then taking CD and replacing it with the value of EF. So you have two different perspectives there, taking the two equalities and making the third equality either through transitivity or through substitution. Alrighty? But not all substitution is transitive. Okay, there are some substitution properties that when we use them, it's not transitive properties. So, for example, let's say we were given AB is greater than CD, right? So AB is greater than CD, and that CD is equal to EF. Well, then it follows that I can take that expression CD out and replace it with the expression of EF. So that means I now have the new statement AB is greater than EF. So because we replace CD with EF. But notice that you can't do that with transitivity equality. Transitivity equality requires two equations two relationships of equal signs, right? So you're going to need two equations. Where up above, AB greater than CD, that's actually not an equation. We call that an inequality. It's because it's not an equal sign between, it's a greater than or less than sign between. So because we say AB is greater than CD, that's not an equation. Transitivity requires two equal signs to be worked with. So we cannot use transitivity in that first one. So let's just put them next to each other and we can watch how transitivity and substitution compare with each other again. So the first statement, measure angle A equals measure angle B, and the measure angle B equals measure angle C, thus a measure angle A is equal to the measure angle C. That's an example where I can use both. I can say that's true by the transitivity property of equality, or I can say it's by the substitution property of equality. So the first one is both transitivity and substitution. But the second, let's read that one. Angle A is right, and if measure angle A is equal to measure angle B, then angle B is also right. That's substitution property because I know that the two measures of my angles are equal. That means whatever, and equality goes a little bit deeper than just the value. It means also properties. It means that the whatever is true about the measure of angle A is also true about the measure of angle B. So because the property angle A already has as a right angle, that means angle B also has that same property. That's only substitution. Notice in the second equation or second sentence, or second statement. Sorry. There's only one equation. That's right in the middle of the sentence, right? Measure of angle A equals measure of angle B. That's only one equation. Transitivity needs two. Substitution can work with only one. Here are some other properties algebraic in nature. You recognize these, such as addition property, subtraction property, multiplication, and division. We'll use it quite often. We actually use addition and subtraction much more often than we use multiplication and division, but when those do arise, we will have them there. And of course, I'm getting a little ahead of myself. Let's talk about the law of trichotomy. Law of trichotomy is something I mentioned briefly in our earlier lesson 1.6, and that's what it says when we talk about the comparison of two values, of having the comparison of a greater than or a less than. Well, law of trichotomy says this, that whenever you bring two quantities together, so for all quantities x and y, then one and only one of the possibilities can occur. Either x and y are the same measure, the same quantity, same value, so they're equal to each other. Or x is less than y, or x is greater than y. And so because of that, you'll notice that we have this relationship of three things happening, thus trichotomy. It's actually looking at three comparisons of our quantities together. And you may not have seen this before. The reason why I'm not sure really the history why they call it a law of trichotomy. I really think it's just kind of um, someone called it that way and it just kind of stuck, and so it's kind of just like a tradition. We call it the law of trichotomy. So down below, say for instance, if we know that the measure of angle A is not less than 90 and the measure of angle A is not greater than 90. Well, remember, the law of trichotomy says that when you bring two quantities together, one of those things has to happen, and only one of those things has to happen. So if it can't be less than and it can't be greater than, then one thing must happen by the law of trichotomy. We can say that angle A is, or the measure of angle ABC is equal to 90. So that's an example of using law of trichotomy by bringing these two quantities, the measure of angle ABC and the measure of the 90 together, and actually comparing them. And if we know one's not less than, and we know it's not greater than, then it has to be equal to. And we'll actually we'll see an example of using law of trichotomy here in just a second. And of course, this is what I was going to mention earlier. And of course, just like our other algebraic properties, there are many others, and we'll kind of mention them along the way, like the distributive property, association property, like the associative property. So as we encounter those will show up. But as far as the postulate theorem handout goes, we'll just stick with kind of the basics for what we need that I know you'll use more often than not than any other algebraic property that we see come through. All right, let's practice using inference again. So what I'm going to do, remember how to make an inference, is you make a statement. And then from that statement, you draw upon that statement something that you want to be true. And it has to be true 100% of the time. And you're using the previous statement to help you do that. And so we want to make sure that it's genuine, meaning that the second statement we make does it actually follow? It does actually follow from the first that we're not just saying something and thinking that something is true. We actually have to have this next segment justifiably true, which means we have to support it with either a definition or with a postulate. So here's our inference down below. It says this. First of all, our statement is AB, the measure of segment AB is equal to the measure of segment CD. Well, thus, the measure of segment AB divided by 2 is equal to the measure of the segment CD also divided by 2. Is that a proper inference? Well, yes. That is actually using the division property of equality. So it does follow because I'm allowed then to say I can divide equals from both sides and I still remain with equals. So AB divided by 2 is going to be equal to CD divided by 2, and that does follow from my first statement. 100% of the time, I'm dividing it by the same thing on both sides. Let's look at another one. The measure of angle ABC is equal to 90 degrees over 2. Thus, the measure of angle ABC is 45 degrees. Well, let's look back at our first statement. 90 degrees divided by 2, that is something that we can simplify. And we mentioned this just a few slides ago, that whenever you simplify something, that is the hammer of substitution. So yes, this does follow. It's called the substitution property. I'm allowed to take 90 degrees divided by 2 and replace it with the 45 degrees. So that is something with substitution involved. This is not transitivity here, so be careful. Transitivity only works with two equations. We only have one in our first statement, and that's actually substitution then. We take the 90 degrees out over 2 and we replace it with 45 degrees. So whenever you simplify, that's our hammer of substitution, so that does follow. Let's do another one. AB isn't larger than CD, thus AB is less than CD. AB isn't larger than CD, thus AB is less. So if I tell you AB is not larger than CD or it isn't greater than CD, does that inference genuinely make AB less than CD? Well, no, it doesn't. There's another possibility. What if AB is equal to CD? So my conclusion that I made in my inference, it's not 100% correct, which means it is not a proper inference. I cannot say that just because AB isn't greater than CD, that I immediately know that AB is less than CD. No, in fact, I actually have two other possibilities. Why? Because of the law of trichotomy. Law of trichotomy says that AB and CD have three possible relationships. Either AB is greater, less than, or equal to. Well, if we know AB isn't greater than, that leaves us with two other possibilities. AB could be equal to CD, or AB is less than. But so by making a statement that thus AB is less than CD, I'm actually making a false statement because I don't know that to be true 100% of the time. And we need our inferences to be true 100% of the time. We need that. Let's do one more inference and then we'll practice something that we haven't seen before on the last slide. So here we go. AB is equal to MN and FG is equal to MN, thus AB is equal to FG. Yes, that immediately follows. We actually can argue this one of two justifications. We can say this either follows by transitivity of equality or by substitution. I prefer to use transitivity of equality here just because that's when I can use it. It follows from the two equations. AB equals MN, FG equals MN. So we do have the two things equal to the same third thing. Thus, the two things must be equal to each other. I'm using Euclid's formulation of the transitive property of equality there. So yeah, that one I would say most often not I would say the transitivity property. However, you could use substitution to argue this. Now on the next slide, don't be shocked in what you're about to see. What you're about to see is we're going to have now chained inferences. Chained inferences. And one of the very first encounters that you've actually had with chained inferences is in your Algebra 1 class. For example, your teacher could have given you an equation and asked you to solve it. And every time you went from one statement to the next, you had to then explain what property you used, whether you used the addition property, division property. That's actually chaining inferences together. You're drawing one truth equation from another. So what we can do with those chained inferences is we can put them into what's called implication tables. So this is a first example of what an implication table looks like. It's an inference chain. It takes previously made statements and it organizes them into two columns, a statement column on the left and a reason column on the right. Now you'll see that I've already helped you out here by filling in the entirety of the statement column. What you're going to help me then fill in is what the reason column is going to look like. So if we take a look at our first two statements, the measure of angle 1 equals 60 degrees and the measure of angle 2 equals 120 degrees. look at the reason column. It says both are given. That's because in all of our inferences so far, I made an initial statement. Those are actually what we call the given statements. And then what follows from those are what we call the inference statements. So statement 3, 4, and 5, those are inference statements that I'm actually drawing from the first made statements, and actually have two made statements here, statement 1 and statement 2. Every time we make an inference, and you've noticed this along the way, not only have we said, yes, it does follow, or no, it doesn't follow, we have justified it along the way. Was it a definition? Was it a postulate? So, as we're going through this inference chain and filling our implication table, every single one of those blanks in the reason column, we're going to need to fill in then with what is the proper justification. So let's take a look then, going from our statements 1 and 2 and making a new statement here in number 3 and justifying it. So in statement 3, I have now the measure of angle 1 plus the measure of angle 2 is equal to 60 degrees plus 120 degrees. What's going on there? Well, measure of angle 1 equals 60, measure of angle 2 equals 120. But now I'm adding 1 and 2 together, and I'm adding 60 and 120 together. That is actually one of our algebraic postulates. That is the addition property of equality. Now, why is it the addition property? The addition property, remember, says that we can add equals to equals, and guess what we get? We get equals from that. So if I take the equals from statement 1 and I take the equals from statement 2 and I add those equals to my other equals, I get equal things, which means that's where I get angle 1 plus angle 2 is equal to 60 plus 120. Let's now move to our next inference in our statement 4. So now I'm saying, well, I can actually draw another truth. I can actually take that 60 degrees and 120 degrees, and I can actually add them together, making 180 degrees. So in statement 4, what then did I do? Statement 4 is not the addition property. Addition property says that I'm adding equal things to each side of my equation. Well, I'm not doing that here. I'm actually simplifying 60 degrees plus 120 degrees, so which means I'm taking that statement out and replacing it with 180 degrees. And anytime we simplify, that is what we call the hammer of substitution. So this is our substitution property, which I'm going to go ahead and write all that out. Substitution property. So that being, right, think about what substitution property is. Whenever I simplify, I can then replace one expression with another expression. And that's where I'm really doing. 60 degrees plus 120, I'm replacing it with 180 degrees. Now, take a look at statement 4. What it now says is that the sum of two angles adds up to 180 degrees. Angle 1 plus angle 2 equals 180. Well, we have a definition for that. We have a definition that says whenever two angles add up to 180 degrees, we call those two angles, now look at statement 5, we call those two angles supplementary to each other. So angles 1 and 2 are supplementary. How do I know that? Because they satisfy the definition of supplementary. So let's take a look then. Oh my goodness. Let's take a look then at our reason statement. And what are we saying here? We're saying it's the definition of supplementary. So that is our definition, and that justifies moving us from statement 4 into statement 5. So this is what we call inference, chaining our inferences, right? Moving from one inference to another, or this whole table we call the implication table, because we're moving from one implication, making another implication, and we continue doing that justifiably until we get to our last statement, which you will practice some inference chains on your worksheet. So on the worksheet, you will practice using just your singular inferences, moving from one statement to another and justifying it like we saw in previous slides. And then in another section, you'll be practicing your inference chains, moving from one statement to another statement to another statement to another statement to another statement until you've arrived to the very last statement within your table and you've justified every single reason along the way. Please be sure you're going to want two things out in front of you when doing your homework assignment. It would be good to have a list of your definitions, and it's also going to be good to have your postulate theorem handout in front of you because those are the tools you're going to be using to help justify along your way. Now, keep in mind, you're only using definitions and you're only using postulates. Do not use theorems yet. We are not yet to our theorem chapter, so we're only justifying things with definitions and our list of postulates. Well, that's the end of our 1.7 algebraic postulates lesson. Please be sure you work on your homework assignment, and if you do have any questions, don't hesitate to email me. With that, be good and do good.